Welcome, everyone. I'm excited to kick off our presentation today on the application of integration. This is the first slide, and it's simply a welcome and an introduction. You'll see the title, Application of Integration, and a brief overview of what we'll cover. Over the course of this presentation, we'll explore various ways integration is used across different fields. So, let's get started and dive into the fascinating world of integration. Now, as we come to the conclusion, let's briefly review what we've covered. First, we looked at the fundamentals of finding areas between curves, which is essential for understanding how to set up our integrals. Then, we explored the volume by slicing, which is a foundational concept for calculating volumes of various shapes. Next, we examined the disk method, a powerful technique for revolving regions around an axis to find volumes. We also extended that idea with the washer method, which helps us handle regions with holes or multiple boundaries. Moving forward, we discussed the volume by cylindrical shells, offering an alternative approach that can be more convenient in certain situations. Finally, we revisited the washer method in more detail, emphasizing its importance and versatility. Throughout this presentation, our goal has been to build a strong understanding of these techniques, as they are fundamental tools in calculus for solving complex volume problems. Remember, mastering these methods will greatly expand your ability to analyze and solve real-world problems involving volumes and areas. Let's take a moment to look at the objectives for today's presentation. First, I want to emphasize that our goal is to thoroughly explain the key points, but I also want to keep it conversational so it feels engaging and easy to follow. As we go through, I'll highlight the most important concepts, making sure they stand out. And of course, I'll connect these points back to the overall theme of the presentation, so everything fits together cohesively. This approach will help us not only understand the details, but also see how they relate to the bigger picture. Now, let's explore the different methods we use to find the volume of a solid of revolution. First up is the disk method, which is perfect when our cross-sections are circles perpendicular to the axis of revolution. It's like stacking disks to build our solid. Next, we have the cylindrical shell method, which considers cylindrical shells created by revolving a region around an axis, especially useful when slicing parallel to the axis. Then, there's the volume slicing method, where we think about slicing the solid into thin sections. It's a more general approach that can adapt to complex shapes. Moving on, the washer method is a refinement of the disk method, used when there's a hole in the middle, like a donut shape. Finally, the area between the curves method involves revolving the area bounded by two curves, giving us a straightforward way to find the volume when the region is between two functions. These techniques are essential tools in our calculus toolkit, helping us analyze and understand the shapes and sizes of 3D objects created by revolution. When we talk about areas between curves, we're essentially looking at the space that is enclosed by two different functions. This concept is really important because it helps us measure the exact amount of space or the area that lies between these curves. To do this, we typically set up an integral that subtracts the lower function from the upper function over a specific interval. The most crucial part here is identifying which function is on top and which is on the bottom, because that determines the limits of our subtraction. This method connects directly to the overall theme of integration, showing how it can be used to find areas that aren't just simple shapes. Understanding these areas between curves also enhances our ability to solve real-world problems where you need to find the space between two boundaries, whether in physics, economics, or engineering. So, mastering this concept broadens our toolkit for tackling complex questions involving space and area. The approximation is getting better as n approaches infinity. Essentially, as we increase the number of strips, our estimate of the area becomes more accurate. Now, imagine dividing the region between the curves into these small strips. Each of these strips can be approximated by a rectangle, where the base of each rectangle is deltax, the width of the strip, and the height is the difference between the functions at that point, which is f, xi minus g, xi. This difference gives us the vertical span of each rectangle, representing the space between the two curves at that particular point. the total area of the region bounded by the curves y equals f, x, and y equals g, x, and the lines x equals a and x equals b can be found by summing up the areas of all these rectangles. Because the functions are continuous and fx is greater than or equal to g, x, over the interval, this sum of rectangle areas provides a good approximation. To improve our estimate, we divide the entire region into n equal strips, making each strip narrower. The smaller the strips, the closer our approximation gets to the true area. When we want to find the actual area, we take the limit as n approaches infinity, turning our sum into a precise integral. This approach is fundamental in understanding how we analyze areas between curves mathematically. All right, now let's look at how to find the area of the region enclosed by a parabola and a line. This is a common problem in calculus, where understanding the shape and the boundaries is key. First, we need to identify the points where the parabola and the line intersect, because those will be our limits of integration. Once we have those points, we can set up an integral to find the area between the two curves. Remember, the main idea is to subtract the lower curve from the upper curve across the interval. This approach helps us accurately measure the enclosed region. By applying this method, we can solve a wide range of problems involving areas bounded by different curves. All right, so here we're considering the approach of using vertical strips to find the area. The key point to remember is that when we do this, we need to split the integration into two parts because the region might have different bounds on each side. But an interesting alternative is to use horizontal strips instead. The advantage here is that the width of each strip is simply di, which can sometimes make the calculations more straightforward. To do this, we need to find the length of each horizontal strip, and for that, we have to express in terms of y essentially. We solve the original equations to get as a function of y, which then allows us to set up our integral more easily. This approach highlights an important concept in integral calculus, the flexibility of choosing different methods, vertical versus horizontal strips, to compute the same area. It's all about selecting the most convenient or insightful way to approach the problem, depending on the shape and bounds of the region we're analyzing. Let's start by sketching the curves, which helps us visualize the area we're working with. Now, when choosing our limits of integration, if we're using dx, the limits will be based on x values. Conversely, if we're using di, they'll be based on y values. Next, we need to find those limits of integration, which depend on how the curves intersect. Deciding whether to use vertical or horizontal strips can make a big difference. I suggest choosing whichever is easier to write formulas for, especially when calculating the length of the strip, or when it reduces the number of integrations needed. Once we've decided on the orientation, we write an expression for the area of a single strip. Remember, if the width of the strip is di, then the length must be expressed in terms of y. If the width is dx, then the length should be in terms of x. Finally, to find the total area between the curves, we perform the integration over the chosen limits. This step sums all the infinitesimal strips to give us the total enclosed area. And that's the general strategy for calculating the area between curves. Let's take a closer look at volume by slicing. Here, we're breaking down the data into specific slices to understand how volume varies across different segments. This approach helps us identify patterns and trends that might not be obvious when looking at the overall data. By analyzing these slices, we can pinpoint which areas are driving growth or facing challenges. It's a crucial step in making informed decisions, as it allows us to target our efforts more effectively. This concept ties back to our overall theme of optimizing performance through detailed data analysis. The more precisely we can examine these segments, the better we can tailor our strategies for success. Let's take a closer look at volume by slicing. This concept is all about understanding how we can analyze data more effectively by breaking it down into smaller, more manageable pieces. When we talk about slicing, we're essentially dividing our dataset into segments based on specific criteria, which allows us to see different perspectives and identify patterns that might be hidden in the overall volume. By examining volume through these slices, we can pinpoint where the most activity is happening, whether that's in certain time periods, geographic regions, or demographic groups. This targeted approach helps us make more informed decisions because we're not just looking at aggregate data, we're exploring the nuances within it. Connecting this to our overall theme, volume by slicing empowers us to drill down into the details, providing clarity and depth to our analysis. It transforms raw numbers into actionable insights by highlighting where to focus our attention for maximum impact. So, understanding and applying slicing techniques is crucial for refining our strategies and driving better results. Now, let's turn our attention to the disk method, which is a powerful technique for finding the volume of a solid of revolution. Essentially, this method involves slicing the solid into thin, circular disks. Imagine taking a curve and revolving it around an axis. These disks stack up to form the three-dimensional shape we're interested in. The key idea is that each of these disks has a certain radius, which depends on the function describing our curve, and a small thickness. By calculating the volume of each individual disk and summing them all up, we can find the total volume of the entire solid. This method is especially useful when the solid is generated by revolving a region around an axis, and it helps us visualize how the volume accumulates layer by layer. Throughout this process, understanding the relationship between the radius of each disk and the function defining the boundary is crucial. In the bigger picture of our presentation, the disk method ties into our broader theme of converting complex geometric shapes into manageable calculations. It's an elegant way to handle many volume problems that might seem complicated at first glance. Now, let's take a closer look at the volume of a disk, which is given by the formula pi r squared times w. This formula essentially describes how we find the volume when a shape is revolved around an axis. The simplest example of such a solid is a right circular cylinder, or simply a disk. Imagine revolving a rectangle around an axis that runs next to one of its sides. That's how this shape is formed. When we talk about revolving a region in the plane around a line, the resulting three-dimensional shape is called a solid of revolution. The line we revolve around is known as the axis of revolution. This brings us to the disk method, a powerful technique for calculating volumes of these solids. It relies on slicing the solid into thin disks, each with a small thickness, and summing up their volumes. Understanding this method is key because it connects the geometric intuition of rotating regions with the analytical tools we use to find exact volumes. It's a fundamental concept that helps us solve many problems involving revolved shapes throughout this course. Now, let's look at how we can determine the volume of a disk. Here, we see that the volume depends on two key dimensions: the radius, which we denote as r, and the width, which we call w. Essentially, the volume is calculated by taking the area of the circular base, so pi times r squared, and then multiplying that by the width, w. So, the formula becomes volume equals pi times r squared times w. Remember, this approach is fundamental when we're working with disks in volume calculations, especially in applications like solids of revolution. By understanding how the radius and width influence the volume, we can better grasp how these shapes behave in three-dimensional space. To determine the volume of this solid, consider a representative rectangle in the plane region. When this rectangle is revolved about the axis of revolution, it generates a representative disk. The volume of this disk can be approximated by considering its cross-sectional area times its thickness. To see how to use the volume of a disk to find the volume of a general solid of revolution, imagine the plane region shown in the figure being revolved around the specified axis. By summing up these disks, small slices from the region, we can find the total volume of the solid. This approach is what we call the disk method, and it's a powerful tool for calculating volumes generated by revolution. So, here we have a schematic representation of the disk method. Essentially, it's a visual way to understand how we calculate the volume of a solid of revolution. The key formula here is that the volume of the solid is approximately equal to the integral from a to b of pi times the radius squared, with respect to x this pi r. X, Squared term represents the area of each circular cross-section, or disk. As we increase the number of disks, which we denote as n, our approximation gets more and more accurate. Think of it like adding more slices to a pie. You get a finer, more precise representation of the shape. So, we can define the volume of the solid as the limit of these sums as n approaches infinity, which leads us to the integral formula. Alternatively, if we want to approximate the volume using a finite number of disks, we can think of dividing the interval into n parts, each with a small width deltax. For each of these disks, we use the radius at some point within that subinterval, denoted as r, xi. Multiplying pi times the square of that radius, and the width deltax gives us the volume of each individual disk. When we sum all these up, from I equals 1 to n, we get an approximation of the total volume. The main takeaway here is that this method allows us to break down complex shapes into simpler, manageable pieces, disks, and then sum their volumes to get an overall measure. It's a powerful technique that connects the geometric intuition with the calculus tools we've been exploring. Now, let's look at how to find the volume of a solid formed when we revolve a region around the x-axis. Specifically, we're considering the area bounded by the graph of y equals f of x and the x-axis, between equals 0 and x equals pi. In this example, we'll use the disk method, which is a common technique for these types of problems. The key idea here is to imagine slicing the solid into thin disks perpendicular to the x-axis. Each of these disks has a radius equal to the function value, f of x, at that point. By calculating the volume of each infinitesimal disk and summing them up across the interval, we obtain the total volume. The formula involves integrating pi times the square of the function, from x equals 0 to pi. Remember, the critical part is understanding that the radius of each disk is determined by the function value at that x, and the volume of each disk is pi times that radius squared, multiplied by a tiny thickness dx. This method simplifies what might seem like a complicated shape into a manageable integral, connecting the geometric intuition with the calculus technique at the heart of volume calculations. Continuing with the solution, from the representative rectangle in the upper graph, you can see that the radius of this solid is r of x, which is equal to f of x. This means that at each point along the x-axis, the radius of the generated solid corresponds directly to the value of our function at that point. Understanding this relationship is key because it allows us to set up the integral for the volume of the solid by revolving this region around the axis. The function f of x essentially defines the shape and size of our cross-sections, which is crucial for calculating the total volume accurately. So, by visualizing this in the graph, we get a clearer picture of how the radius varies and how that impacts the overall volume calculation. Let's break down the steps to find the volume of the solid of revolution. First, we simplify the problem. This helps us manage the calculations more easily. Next, we move on to integrating the functions to find the volume, which is a crucial step in the process. After that, we apply the disk method, a powerful technique for calculating volumes of revolved solids. By following these steps, simplify, integrate, and apply the disk method, we can determine the volume of the solid of revolution. This slide continues our example, showing how these steps come together in a practical problem. Remember, the key idea here is to break down complex shapes into manageable parts and then use integration to find the volume. Now, let's take a look at the washer method. This is a powerful technique we use to find the volume of a solid by revolving a region around an axis. The key idea here is to imagine slicing the solid into thin washers. Think of like a stack of coins with a hole in the middle. Each washer has a small thickness, and by summing up the volumes of all these washers, we can find the total volume. The most important concept to grasp is that the volume of each washer depends on the difference between the outer and inner radii, which change depending on the shape and the axis of rotation. This method is especially useful when the region being revolved creates a hollow or ring-like solid. Connecting this to our overall theme, the washer method extends our understanding of volume calculation beyond simple shapes, giving us a versatile tool for tackling more complex problems. So, the volume of the washer is given by this formula. Pi times the difference of the squares of the outer radius r and the inner radius r, multiplied by the width w essentially. If you think about it, r and r are the inner and outer radii of the washer, and w is its width. This helps us calculate the volume when the washer is formed by revolving a rectangle around an axis. Now, an important point to remember is that the washer method is an extension of the disk method. Instead of just disks, we now use washers to account for solids with holes in the middle. So, instead of a solid disk, we think of a washer with a hole in the center, which allows us to handle more complex shapes. This approach is very powerful because it allows us to find the volume of more intricate objects by replacing the simple disk with this washer shape. It's a key technique in the broader context of calculating volumes of revolution, especially when the shape isn't just a simple solid. When we revolve a region about its axis of revolution, the volume of the resulting solid can be calculated using an integral. The key idea here is that the integral involves two parts, one for the outer radius, which is r of x, and one for the inner radius, r of. The volume element is essentially a washer or a disk with a hole in the middle. To find the total volume, we take the volume corresponding to the outer radius and subtract the volume of the hole, which is given by the inner radius. This subtraction ensures we only measure the solid material, not the empty space in the middle. When applying this concept, consider a region bounded by these two radii, outer radius r of x and inner radius r of x. This approach is called the washer method, and it's really powerful for dealing with solids that have hollow parts. Overall, this method helps us break down complex shapes into manageable slices, making the volume calculation much more straightforward. Now, let's move on to finding the volume of the solid formed by revolving the region bounded by the graphs of these functions about the x-axis. This is a classic application of the washer method, which is particularly useful when our solid has a hollow center, like a washer or a ring. The key idea here is to think of the volume as being made up of many thin washers stacked along the axis of revolution. Each washer has an outer radius and an inner radius, which correspond to the distances from the axis to the outer and inner boundaries of our region. By integrating the areas of these washers from the starting to the ending point of our region, we can find the total volume of the solid. This method is very powerful because it allows us to handle regions with holes or gaps, which the disk method can't always accommodate. Remember, the critical steps involve identifying the correct radii, setting up the integral carefully, and ensuring we're integrating over the right interval. This example really highlights how the washer method extends our ability to find volumes of more complex shapes. Now, let's look at how we apply the washer method. The key idea here is to consider the inner radius and the outer radius of the region we're revolving. These radii define the circular cross-sections that make up our solid. When we set up the integral, we're integrating between 0 and 1, which corresponds to the bounds of our region. In Figure 7.2, you can see clearly how these radii are defined. Notice how the inner radius is the distance from the axis of rotation to the inner edge of the region, and the outer radius extends to the outer edge. This setup allows us to calculate the volume by summing up these washers, or disks with holes, across the interval. And in our example, we've worked through the solution step by step to illustrate this process. So the most important takeaway here is understanding how to identify the inner and outer radii and how they fit into the integral when applying the washer method. This approach is really powerful for handling volumes of revolution with hollow regions. Now let's move on to the next step, integrate to find the volume. This means we'll set up an integral that covers the entire region we're interested in. Once we've established the correct limits, we'll perform the integration to determine the total volume. Next, we'll simplify the expression we get after integrating. Simplifying is crucial because it helps us interpret the result more easily and ensures our answer is as clear as possible. Remember, in this example, we're continuing from where we left off. So it's important to see how these steps fit into the overall process of calculating volumes with integration. By mastering these steps, integrating and simplifying, we're building a solid foundation for solving a wide range of volume problems using calculus. Now, let's continue exploring the washer method with this next slide. Here, I want to emphasize that the washer method is a powerful technique for finding volumes of solids, especially when our cross-sections are hollow, like washers. One key point to remember is that the volume is calculated by integrating the difference between the outer and inner radii squared, multiplied by pi. This essentially captures the idea of subtracting a smaller, hollow cylinder from a larger one. As we go through these steps, keep in mind how important it is to identify the correct bounds and the radii functions, which depend on the geometry of the problem. Connecting this to our overall theme, the washer method helps us handle more complex shapes where simple disks aren't enough, broadening our ability to analyze three-dimensional objects. So, always pay attention to how the inner and outer radii change with respect to our variable. And remember that setting up the integral correctly is crucial for accurate calculations. So far, we've looked at axes of revolution that are horizontal, and in those cases, we integrated with respect to x, but now, in the next example, the axis of revolution is vertical. And because of that, you will need to integrate with respect to y instead. This change means you'll often end up with two separate integrals to compute the volume accurately. Remember, the key here is understanding how the orientation of the axis affects your method of integration, especially when using the washer method. This is a great example of how adapting your approach based on the problem's geometry can lead to correct solutions. So, keep in mind that switching from a horizontal to a vertical axis isn't just a small change. It often involves reevaluating your limits and the functions you're integrating. Now, let's look at how to apply the washer method to find this volume. First, we simplify the expression and set up the integral. Remember, the key here is that we're summing up the volumes of many thin washers. Using the definition of the inner radius, we can establish two integrals to accurately account for the space. In this example, finding the inner radius involves determining the relation for y for the region shown. The outer radius is straightforward. It's just r equals 1. This simplifies our calculations because the outer boundary is fixed. So, when we're setting up our integral, we're considering the volume generated by revolving this region around the y-axis. The region is bounded by y equals x squared plus 1, y equals 0, x equals 0, and x equals 1. Since we're integrating with respect to y, it's essential to understand how the radii relate to y because of the geometry. We need two integrals, one for the inner radius and one for the outer. The inner radius depends on x, which in turn depends on y, and this is where the relation for y helps us. By establishing these two integrals, we can correctly compute the total volume of the solid. This approach highlights the power of the washer method, breaking down a complex shape into manageable slices that we can integrate easily. Overall, this step is crucial because it connects the geometric intuition with the algebraic setup, enabling us to find the volume accurately. Now, let's move on to slide 29, where we focus on volume by cylindrical shell. Here, we're exploring a different method for calculating volume, especially useful when dealing with revolutions around the y-axis or other complex shapes. The key idea is to conceptualize the solid as being made up of many thin cylindrical shells. Each shell has a small thickness, typically represented as a differential element, and its volume can be calculated based on its circumference, height, and thickness. What makes this approach so powerful is that it often simplifies the integration process for irregular shapes or when the disk method becomes cumbersome. We essentially integrate the surface area of these shells over the interval of interest to find the total volume. This method connects to our overall theme of mastering multiple techniques for volume calculation, giving us flexibility depending on the problem's geometry. By understanding the volume by cylindrical shell, we expand our toolkit, allowing for more efficient solutions in a variety of scenarios. Let's delve into the concept of volume by cylindrical shell. When we're calculating the volume of a solid of revolution, one effective method is to use the cylindrical shell approach. This involves imagining the solid as being made up of many thin, hollow cylinders or shells. Each shell is defined by its radius, height, and thickness. The key idea here is that by integrating the volume of these shells across the interval of interest, we can find the total volume of the solid. The formula takes into account the circumference of each shell, which is 2 pi times the radius, multiplied by its height and the thickness. This method is particularly useful when the typical disk or washer methods become complicated, especially with certain functions or regions. It allows us to set up the integral in a way that's more straightforward for some problems. In the context of our overall presentation, understanding the cylindrical shell method broadens our toolkit for solving volume problems. It highlights how different techniques can be applied depending on the shape and the axis of revolution, ultimately giving us more flexibility and power in our calculations. Let's wrap up with some final thoughts. In this conclusion slide, I want to emphasize the key points we've discussed throughout the presentation. We've explored how these concepts are interconnected and how they fit into the bigger picture. The main takeaway is that understanding these core ideas helps us make better decisions and implement more effective strategies. Remember, the overall theme has been about continuous improvement and staying adaptable in a changing environment. By applying what we've learned today, we can move forward with confidence and clarity. Thank you for your attention, and I look forward to seeing how you put these insights into practice. We hope this presentation has been helpful for you in understanding how to find area and volume using different methods, such as the disk, washer, and cylindrical methods. Throughout this session, we've explored how these techniques allow us to approach complex problems with confidence. Remember, the key is to choose the right method based on the shape and the problem at hand. By mastering these methods, you're better equipped to analyze and solve a wide range of real-world and mathematical problems. Thank you for your attention, and we wish you the best in applying these concepts in your studies and beyond.